All right, let's start the second session on today, and we can resume from where we left on the layer 2 multicast. And on the layer 2 multicast, we discussed on the IGMP functionality, Internet Gateway Management Protocol, Internet Group Management Protocol, and we have been discussing version 2 operation, and I had a explanation on the IGMP snooping functionality, which is layer 2 and layer 2 switches need to support on IGMP, which is the version layer 3 protocol, and it's having the modern day switches having IGMP route processors, and now the modern day switches are quite capable of supporting IGMP snooping functionality, which is to support to prevent flooding in the layer 2 networks of the multicast. Okay, let's move back. Let's move forward with the layer 3 multicast. So let me go back to the initial reference diagram. Okay. We were discussing on the layer 2 host to router signaling protocol, which is the layer 2 multicast discussion, and now we are discussing on the router to router, which is the layer 3 multicast functionality or layer 3 multicast operation. Okay, I think we have been discussing on the trees when you're having discussion on the spanning tree protocol, which is to avoid loops on the switches or the layer 2 networks. The loop avoidance protocol is spanning tree protocol, and we discussed on the modern data centers having factory or factory protocol or leaf spine architecture to get the full bandwidth for the implementation. Now, again, there is another discussion on a different kind of tree architecture, which is related to the multicast. So, initially we discussed, I explained you that multicast traffic usually goes from source to the destination, similar to the excuse me, similar to the unicast source to destination. The similar data path will follow from the source direction of source to the destination. But for the multicast, you need additional control plane to traffic sent from the source to the receivers who are intended. You need to have mechanisms to filter your receivers based on the intention to receive the traffic. And there's something called tree building process in the multicast to filter the dynamic requirement of receivers. So there is a tree again in terms of the delivering from source to the destination for the traffic, but tree building process happens usually the opposite side, which is from the receiver to the sender, and receiver starting the requirement to receive multicast by sending IGMP messages from upstream routers. Then upstream routers will be starting sending their router-to-router signaling protocol to build trees from source to the destination, or based on the receiver to source request. So basically, the tree is the root of the tree in this particular case. Source when multicast is originated from the sender, or the channel multicast traffic originated from the sender. The leaves are the leaves representing the receivers, and the root representing the source, and intermediate routers representing the core and the branches for the interconnection between source and the receivers. So in this case, mechanism for transmitting information from single source, which is the root in this case, to many receivers, which are the leaves of the tree, and single copy of the datagram from source to datagram is sent from the source and then replicated through the tree to receivers who are intended to have the traffic. Then there are two types of trees. The first one is source tree, which is separate tree, which is addressing the source network for sending the traffic up to a point. That point named as rendezvous point. Okay, there is a separate tree from source to the rendezvous point, which is an intermediary point to join the two trees. Another tree is built on for the receivers to share from source to the from rendezvous point, which is the intermediary point, to the receiver host. So that is called as shared tree. It is shared, named as shared tree, which means it's shared among all the receivers. Source is only sending to the first of router or the rendezvous point, whatever it is intermediary point. Okay. So we are learning that you need the tree structure to represent a control plane from control plane to transfer traffic from multicast source to the receivers representing as the leaves. The source will be the root there. The tree building start from the not from the root. Tree building start from the receiver side, receiver signaling its requirement, and it's aggregating and forwarding up to the level of source, network level of source. So there are two types of trees. One is representing source side of the tree, source side, which is connecting to the intermediary point, mostly the rendezvous point. And another tree is there, subtree is there for the shared tree as a shared tree, which is to interconnect intermediary point, which is the rendezvous point connecting to the end host. Okay, this is the full picture in terms of now we are using a tree to send a dynamic tree to send traffic from source to the receivers who are on the leaf. Okay. So let's remove the real tree and represent by using the logical tree in this case. So now your source is sending single copy of a datagram which is multicast, and there are three branches here. Now the receivers are there on all the branches. Now it's replicated at each branch because receivers are there on all three branches. Now again, there are now more sub branches there, or more each branch or network segment connect. Let's assume that these three branches are three network segment and connecting different hosts. The most right side having three hosts, and the middle network segment having 1, 2, 3, 4, 5 hosts, and the left side branch having 4 hosts. So since there are a number of hosts or number of receivers, now the single copy replicated to 3 branches, and 3 branches having different number of receivers all get replicated by the switch itself on the network segment and getting the messages by all the receivers who are intended or signaled previously to receive the message. This is a kind of virtual tree you can think of based on the real tree I represented on the previous diagram. The mechanism for transmitting, transmitting from source to destination following the tree architecture or tree built for the multicast transmission. The tree is the control plane structure. the data flows through the data plane, which is built by control plane. So you can see the direction of traffic from source to the receivers by the black arrow. And that is, let's discuss further on what's this source tree kind of functionality without separating it. Usually, traffic sending, you can see the simplest form here. The source sending traffic to its connected network segment or the VLAN. Then it will forward to the first of router from the source space perspective. Since you can see that there are several intermediate routers and last of routers which are connected couple of end host or the receivers. But there are some routers who are not connected any receivers, so you are not sending or replicating traffic to those unintended path who are not having receivers or not received, not signaled by the receivers. So you can see the rightmost couple of routers, even though those are connected to the first of router connected to the source, not replicating traffic to those sites, but it's replicating only to the segments where the receivers are connected. And you can see that from source to the first of router, then there is an intermediate router branch, and it's for replicated there, and there are two branches after the second router, and the second router will be replicating both the branch connected first routers, next of routers, and one is directly connecting to the next top router. Another one, there is another router, and both the receivers are getting replicated traffic until at the point of this connection. So you can see that no traffic travels to the left side because there is no request made from those routers or not connected to the receivers. All right, simplest form of tree is receiver requires knowledge of source and traffic travels from source route to the receiver, shortest path taken. Because you can see that the shortest path taken, otherwise you can go to the right side routers and go into a loop or go into a different path. The shortest path usually selected by using unicast routing protocols. Unicast routing protocols are capable of finding the shortest path. So to find shortest path, usually the multicast routing protocols dependent on unicast routing shortest path algorithms. All right, that means the packets replicated at each branch. You can see that there are receivers on the upstream branches or down. Then the packets replicated accordingly. There are no receivers on the path. It's not replicated to that particular path. Usually, these route forwarding entries are represented as S, G. S means source and the G means group. So that is usually called as M route, which means multicast route, not represented as unicast route. As I shown you previously, it's representation by the operating system, and the network operating system is somewhat different. The Linux and the Microsoft, as I shown you, the both multicast and unicast represented in a similar way, but for the network, it's maintaining the state as well, state table. So therefore, the M route entries, multicast route entries having another form, which is to update the state of the multicast route, and it's represented with S, G. So when you see a route with the S, G, that means it's based on the source tree route, which means you have a source address and the group address on all these routers configured here in addition to the so it's representing this traffic sending from this particular source IP address, which is an unicast IP, unicast IP address, and there is a group G representing the multicast group address, something like 239.5.6, which is within the multicast group address range. So that is how you are representing the source tree. Provides optimal routing, which is the shortest path based on the unicast router. So these G routes are representing from source to receiver shortest path tree, and those are named as source tree. So in this particular network, there is no rendezvous point, just with the two trees. Usually, rendezvous point require if there is a immediate combination or joint requirement between source tree and the receiver tree, which is the shared tree for among. So in this case, there is only one tree. It is a source tree, and all these routers, intermediate, the first of routers, last of routers, and intermediate router, all the routers having SCMG multicast route entries. It included source and the group address, multicast source unicast IP address and group multicast IP address. The route entries, multicast route entries, if you check on the devices. And there is something called requirement when you are implementing the best practices on the modern day networks. The source tree is not the only implementation. Usually, there are several benefits of implementing intermediary point, which we usually call rendezvous point. I think this is an Italian pronunciation. The exact pronunciation are not similar to these spellings. It's usually spelled as a rendezvous point, which is the meaning of meeting points. If people are meeting in a certain point, that's usually identified as a rendezvous point. In this case, both source tree from the source side network and receiver side network, which is the shared tree among the receivers, are usually meeting at the rendezvous point, which is a different dedicated router for the functionality. So that is named as rendezvous point, which is the green color on this diagram. So usually, as I mentioned before, usually source trees are having the route entries with the G source IP address and the group IP address. Source having unicast IP address, group having multicast IP address on the routing entries, multicast routing entries. So this rendezvous point is the intermediary one. It's having both G, which is the source route, which is a source tree. For an example, you can see that rendezvous point is the usefulness. One of the important aspect is rendezvous point can handle multiple groups, cater for the multiple groups. In this particular diagram, you can see there are two different sources, the orange color source and the yellow color source. There are two servers, orange source and the yellow source. So the first of our router from the orange source sending its first of router and connecting with the second of router or the next of router, then the rendezvous point. That's the path, source route or the source tree path for the orange. But for the yellow, it's directly connected to the one of the routers, and it's has the direct connectivity with the rendezvous point for the yellow feed or yellow channel. So there are two different multicast groups, two different hosts, and you can nominate both the first of routers configure to send traffic to the rendezvous point. That is the source tree for the orange have a separate tree, the yellow has separate tree. So two different groups. Now both the trees combine at the rendezvous point, and there are receivers there onwards. So the orange color path and the yellow color path terminated at the rendezvous point from the source. There are two sources there, and two multicast channels there, two different group addresses terminating at the rendezvous point that that aggregating the sources. So that's called source tree. Now, then thereafter, after the green rendezvous point, there are receivers. Certain receivers are subscribing for the orange color multicast group or multicast channel traffic, and certain machines are some other machines requesting the yellow color multicast group traffic. So then, or two different the receivers need to share that network and get the corresponding traffic or corresponding stream from the rendezvous point router. So that is shared among all the receivers, and as well as you can share among all the multicast groups as well. Let's say if there is a client or receiver require both the streams, it's possible through the shared stream sending from the rendezvous points onwards. So now you can see that there are two segments, one for the sources, one for the receivers. The source tree is connected up to the rendezvous point as the name identified as a source tree, and it's having as previously mentioned, it's having S, G routes, which means you know the source and you are sending you know the group when you are sending, and aggregated at the rendezvous point. But after the rendezvous point, there are only you don't need to know the source. You just need the multicast group to be forward and only representing the group address. So those routes are represented as *.g. So you don't identify the source, but you are identifying just the group to be forwarded there onwards from the rendezvous point. So you don't need to know the source. So that's called as the shared tree, because you are not defining the source at the point onwards. So let's discuss the bullet points. Root is a common point, which is the rendezvous point, many multicast groups at RP. So all the multicast groups terminated, and you have source trees there, which is the S, G in multicast route entries. Receivers join RP, and receivers intended to get the traffic from all those sources, not joining directly with the source first stop router, but joining with the rendezvous point shared tree. Then sources transmit to, not directly transmitting to the receivers as on the previous case, but sources transmitting first to the rendezvous point, then rendezvous point replicating it to the intended receivers from there onwards. There are no receivers, it doesn't replicate, it's dropping the traffic and signaling it to the sources. There are no receivers. And so because source tree usually require S, G several entries, because if there are several sources, you need to have many route entries such as S, G. But since shared tree not required several entries, even because you are not considering the sources to be identified on your multicast route entries, your group addresses are the only matter here on the shared tree. So you have *.g in routes only on the shared tree segment of the network routers. If you check the routing tables, you can see *.g routes on the shared tree routers, and which is after the rendezvous point. Before the rendezvous point, those are S, G routes, which are representing several routes based on the different source IP addresses, the multicast network. Okay. So let's go back to so this is so it is quite clear on the tree structure. The multicast to be forward or out, you need to have a control plane trees to be built based on the request from the receivers, and the source to the rendezvous point location or shared point. You can have the source trees, and there onwards you have shared tree for the receivers. The importance of having rendezvous point, it is difficult. It is easy to manage if you are having several multicast groups. You just need to configure one router as a rendezvous point, and your all the configurations on the different multicast group included there. And it is easy to troubleshoot as well if you are segmented the network in this way. And again, another importance is now you can implement security policies by using these rendezvous points. So you can block certain receivers getting it and something like that. Can be security policies easily implemented by using intermediary point, which is the rendezvous point, but source tree it is a bit difficult. So let's go back to the layer 3 multicast, which is the multicast routing. We discussed the layer 2 multicast based on the host to router signaling protocol, which is IGMP, Internet Group Management Protocol. And it's only necessary when you are communicating between host and the first of router. And thereafter, the layer 3 network require another set of protocol, which is the router to router signaling protocol. We discussed this initially, that routing protocols are named as protocol independent multicast. There are three variants we discuss, protocol independent major versions. So let's start on the router to router signaling protocol. Protocol independent multicast is used by router to notify an upstream router that it wishes to receive, like the receiver computer. So the receivers signaling the interest to receive by using IGMP to the first stop router. The first stop router then signaling to the next stop router or upstream router interested to receive multicast traffic from this particular group. So that is the router to router protocol, and the protocol independent multicast functionality is based on that. And again, it's the wishes to receive and stop of receiving also can be signaled by using PIM for a given group address, given multicast group address. Three main classifications of protocol independent multicast. First one is any source multicast. There are three submodes of any source multicast, which means any source can send these multicast source IP, irrespective of the source IP, you can forward to two receivers. So three submodes. First one is dense mode, sparse mode, and combination of there is a sparse dense mode. Usually it's work on sparse mode. If there is a failure on the sparse mode, then the fallback mode is dense mode. And there is a special protocol, as we discussed, the further optimization with the shortest path, which is the modern day protocol, source specific multicast, PIM-SSL. Protocol independent multicast is a subset, there is a subset of it with the optimal performance, saying that source specific multicast. We can discuss that later. And there is another variant which we call as bidirectional. Mostly this is important when you are having a requirement like conferencing or the CCTV implementations to traverse both the directions, not the unidirection from source to receiver. There are certain sources who are required to receive the traffic as well. So in that case, we can consider implementing based on the use cases bidirectional, bidirectional. So there are three main types: any source multicast, source specific multicast, bidirectional. The classifications are dense mode, sparse dense mode for the any source multicast, which is called ASN. Okay, are there any questions until this point before we move forward? All right. Let me highlight few key points here. So the protocol independent multicast is between only between the router, which is a router to router protocol, and these some of these modes are the Cisco specific, which is the dense mode is a legacy. The sparse and dense mix modes are legacy as well. Sparse mode usually industry standard, and most people implemented any source multicast by using sparse mode. There are situations if you need fallback, you can implement sparse dense mode with the Cisco routers. And dense mode is quite suboptimal, and it doesn't have a rendezvous point, and it's something like the flooding or not optimal as pass mode by using the rendezvous point. The source specific multicast is the most modern one. It doesn't require rendezvous point to optimize, and it's provide the security features and the best security implementations for the modern day networks. And the bidirectional is only for the specific use cases like the CCTV or conferencing kind of a thing for the optimization. Most of the traffic for the multicast are the one-to-many traffic, usually based on any source multicast or source specific multicast. Right, router to router signaling again. Let's discuss bit more into the concept. Each PIM router, the protocol independent multicast configured or multicast enabled router, forms a neighbor relationship with the adjacent the next stop routers. The PIM routers using the initial message will send a join message. Message will send as hello message for every 30 seconds with a keep alive functionality included. When a PIM router wants to receive a multicast stream, it sends the PIM join message. So keep alive message is something like hello, sending in each 30 seconds by default. And PIM router wanted to receive a multicast stream, it's sending to the sending ping join message towards the IP address of the multicast source. And PIM router wants to stop receiving multicast stream, it send PIM prune message. So joining and pruning is the function of building the trees here. So if you want to join the tree or expand the tree, you are sending join message with the preference to join the tree by for certain network segment, which is downstream to the router. If you want to remove receiving the multicast, since there are no receivers downstream, then you are sending the prune message to remove your branch from the tree. So that is the usual way of working. There are three aspects here: sending hello message by the protocol independent multicast router to maintain the status or the keep alive between the next stop routers. And if you want to, if you haven't joined from multicast stream traffic to be received, then you need to send join message. If you want to exit from receiving the message, then you are sending the prune message. So joining and pruning is the process to build the trees and maintain it by hello keep alives, sending each 30 seconds to make it dynamic. All right, let's so it is something like this. So the router to router signaling and sending a join message to join here. If downstream host are sending IGMP request, then upstream the first stop router will send join message based on the request received from the downstream with the IGMP, and initiating the IGMP join message to the next stop router, which is the shortest path based on the because there are two routers here in this diagram connected to the first stop router, but it selected only one based on the unicast routing table, which is the shortest path to the source. Okay, that's mainly about the introduction of layer 2 multicast and layer 3 multicast. Now we are more towards, these are the reference book I previously shown you. Okay. This is the session we are starting now on the multicast troubleshooting. So fundamentals have done. Now we are starting on the troubleshooting section for both the layer 2 and layer 3 multicast. So as I mentioned, the layer 2 multicast is based on IGMP. We were discussing IGMP 3 variants, version 1, version 2, and version 3 will be explained. I simulated that how version 2, which is the normal practice on the industry, operates. And version 1 is not having this the leave signaling. If any host want to leave from the multicast receiving group, and it's not facilitated on the version 1, so there is no. So version 2 has that enhancement. Version 3 have further implementations like security and all those things are there. The routing, then we can discuss on the troubleshooting on the layer 3 multicast. Especially I'm targeting not the protocol independent multicast pass mode and the source specific multicast. And then IP multicast troubleshooting methods will be discussed in detail. And IP multicast troubleshooting best practices and rule of thumbs will be discussed at the last on this multicast troubleshooting sections. Then I'll be covering IP multicast security implementation on the another session. So most probably we can cover many of the multicast troubleshooting topics today. Okay. All right, multicast, the current multicast support for the solutions, usually the industry best practice or the usual practice. The layer 2 multicasts are mostly covered by implementing IGMP version 2. So IGMP snooping should be implemented there, as I mentioned, the IGMP courier, the layer 3, and IGMP is a layer 3 protocol. You need to have special IGMP route processor to filter the IGMP traffic, otherwise it will be flooded. And you can configure IGMP snooping couriers on the IGMP version 2 to prevent that and configure with the best practices there. And then multicast routing, the layer 3 multicasts, usually I'm discussing the more details on the best practice as a PIM's pass mode for the current day implementations. The previously, about decade back, by default, most of the switches are IGMP snooping off more than a decade back. And the multicast routing protocol was dense mode, which is suboptimal. Basically, multicast flooded on the layer 2 as well as occasionally on the layer 3 protocol independent multicast dense mode. These are the worst ways to do it, but that's how it started in terms of multicast switching and routing. The later optimize with the current day implementations such as IGMP version 2 and PIM's fast mode. Okay, but there is a next gen as well, and this is the best in terms of modern multicast support for solutions, especially on the demands of security as well as the further optimization on the latency or the shortest path. The multicast switching mostly recommended or later multicast the next gen implementation or the most modern implementation preference is IGMP version 3. For an example, latest operating systems by default supporting version 3 and backward compatible with version 2 as well. Even the switches nowadays coming with the by default version 3 support, and the operating systems like Red Hat, SUSE or the Microsoft all operating latest versions are by default coming with the IGMP version 3 support, and it is backward compatible with IGMP version 2 as well. You can force it to back version 2 if there are complexities. Multicast layer routing, which means layer 3 multicast. Usually the next gen is mostly again, you can keep sparse mode, but the better one is source specific multicast. So you can think of implementing source specific multicast on your next gen with the better security and better optimality in terms of shorter paths. So why the network multicast protocols support recommended in terms of modern day? The latest operating systems by default, as I mentioned, supporting version 3. The latest switch models supporting version 3. The business and technological architect advantages are there in terms of it's usually without source specific multicast or IGMP version 3, you can't filter the sources. So which is a kind of security implementation. You can have a rogue source on the previous gen, but you can eliminate that by implementing IGMP v3 and source specific multicast. Multicast group IPs are preserved because there are situations like certain groups you cannot use and preserve for the other functionalities. If you want to share the group address among several different channels, then it's possible with this modern implementation. So lack of group addresses may not be an issue if you are using these modern day protocols. Reduce the overhead of non-functional features like time synchronization, and all those features can be easily implemented with this IGMP v3 and all those these two modern protocols. The less control plane traffic overhead, because it is not because you are not maintaining a separate shared tree. It is not suboptimal and optimal control plane traffic or less control plane traffic, because it's handled by all the host and routers by itself by the better implementation. Optimal data plane traffic path selection. With the shortest path selection is much better with these new protocols. And the security features, definitely you can make an access list for the source and destination receiver combinations to restrict the receiving groups. So it's provided only with the IGMP version 3 and the source specific multicast. Again, there is no harm in implementing version 3 because it's backward compatible with IGMP version 1 and version 2. All right. So I just thought of comparing version 1 and the standardization between version 1, 2, and 3. So how all the usually hosts are communicating with the router, as I explained before, it's by using group membership. So group membership, this is an example group 224.1.1 sending a report, and it's received by the first of router, and it will handle the joining process and as well as keep alive process on the IGMP version 1, 2, and 3. All are similar in this case. If there are 3 hops on the network segment, if host 1 sending a message is sufficient enough for all to entire network segment to join the group and handled by the first of router. Sorry. IGMP versions, the version RFC, so standards mentioned here with the numbers for your reference. And the version 1 specified was the first the initial protocol for the IGMP, which is the widely developed version at the time, which is the first version, became an internet standard for a long time. Then thereafter, the much better version received with the version 2, and it's having the lower leave latency because it's not based on the expiration of timers, but the any host can signal I just need to exit from this group. Otherwise, it's automatically by silently exiting, and router need to follow up for 3 times and then expire based on the timer expiration. So version 2 implemented the low leave message, and you can leave any group quite fast, which is optimal. Otherwise, you are receiving unnecessary traffic. That's the enhancement against version 1 at the time of after the implementation of version 2. Then version 3 has more features, which is the modern day protocol for the next gen or the latest one. It's quite capable of handling the source filtering. You can filter the source, and the interested receiving packets, the ability to system to report interested receiving packets only. You can filter by ACLs, and you can give the control to uh, uh, the developers as well. And again, source specific multicast handle by different, not like version 1 and 2. There is a different process to handle uh, by using a different IP group control multicast group address to support version 3 functionality. So these are summarization of different 3 different standards for the IGMP, and the enhancement by each version. Okay. Another representation in terms of host to router signaling. Now, the host 3, which is sending the IGMP report to join the group, and this is how it's maintained by with the with initially the signal sent. Let's say let's go to the first diagram. Initially, only one the host number 3 signaled joining 224.1.1 group address, but router again couple of other machines getting receiving the message. Then if 2 of the machines, H3 and H1, sending a query, it has sending a query to router send periodic queries to verify whether all the hosts are receiving this. So the only one host is responding to as a follow-up to the follow-up, and I still need this traffic. This is the way it's the router is following up whether there are any intended receivers based on the timers. So this particular slide showing that follow-up message and how each host is responding. The 2 hosts are not responding, and the 1 is responding because that's the one. H2 is the one now still wanted to have the traffic. And this is the leaving process implemented at the IGMP version 2. The first 2 slides are on the version 1, 2, and all 3. Version 1 and 2 both operating. Additional functionalities leaving a group by signaling from the host message. So we explained that in detail on the few slides before. And this is how it's operating. Usually host send the leave message to 2240.0.2, which is to communicate the local routers only. There are multiple routers, all routers getting this message. If you send 224.0.0.1, it means you are sending message to the routers as well as the host. In this case, the leave message only sent to the routers by signal by host number 3 in this case, and it want to exit from the 224.1.1.1 group address and send into the reserve group address 224.0.0.2, which is the control reserve group address here by all the routers. This case only one router. If there are 2 routers for the backup, both the routers receive this. Router sends group query with requesting 221.1.1, which is the multicast group you want to receive traffic, and no IGMP. So this is how usually the signal in the leave message. Then router will follow up if there are any other host require multicast by sending another query, group specific query, especially to 224.1.1 group only. There can be more groups with the more applications, but just exit the last one user signal leaving this, the router following up if there are any other users by sending a query to this particular group address which H3 want to exit. If no IGMP report received as a response to the follow-up by the router, then after 3 seconds, the timers will expire and router will no longer forward the traffic to this particular network segment. That is the functionality implemented in the IGMP v2. If you are troubleshooting, you need to understand this process by taking captures and monitoring the traffic on the multicast IGMP troubleshooting stuff. And the version 3 having more advanced features like enable source specific multicast. The IGMP version 3 individually have more features but more optimal to implement multicast routing with the source specific multicast. So layer 2 multicast, you can have IGMP version 3. Some of the functions need to be combined with this implementation of routing layer 3 multicast routing protocol based on source specific multicast. You can't get the full feature set by implementing IGMP version 3 plus sparse mode multicast or any source multicast. You need to implement multicast routing with the source specific multicast with the combination of IGMP version 3. Then only you can get these benefits like include exclude source list, like by using access control list, you can implement source based security or filter the security, filter the sources. Enable host to listen only the specified subset of sources sending to the multicast. You can enable host to listen only to the specified subset of sources. You can define the sources with the limitation by different criteria to filter it up. And the IGMP version 3 stack required in the operating system. The operating system support required for the IGMP version 3. All the operating systems sometimes may not support version 3, but all modern operating system not support only version 3, but backward compatible as well. By default, it's enabled. If you are having old applications, you can still, if there are complexities or any specific issues, can consider downgrading or disabling version 3 and enabling only version 2. Applications must be rewritten to use IP. Some of the features, if applications are not supporting to use these advanced features by IGMP version 3, you need to customize your communication layer of applications. Requires the operating system API with the IP multicast listen. So those are few important points if you are migrating from the IGMP version 2 to version 3 with the advanced feature support. Okay, version 3 having, I was mentioning that the previously the control plane multicast groups to communicate between routers and host having separate addresses, which is 224.0.0.1 and 224.0.0.2 to communicate with routers and the host. This IGMP version 3 have separate group allocated, which is 224.0.0.22 to handle the multicast group IGMP group state tables and maintain access control list and all those functionalities. So this is quite interesting because when if you are troubleshooting by taking a Wireshark capture, if you notice 224.0.0.22, then you can see that IGMP version 3 implemented there when you are troubleshooting. Based on your packet captures, you can find out what are the IGMP versions implemented, and the Wireshark automatically, the packet capturing, you can classify what are the protocol implemented based on these IP addressing ranges as well. The Wireshark can identify GNP version 3 separately based on its packet structure and the IP addressing schemes. And you don't need to suppress or the timer-based operations for the expiration, and which is suboptimal for the IGMP version 1 and 2. So this is quite efficient in terms of its functionality. You can tune further on the response intervals and optimize for the better latencies, the better functionalities by using IGMP v3. So this is the usual process of IGMP version 3. You can see the version 3 reports are addressing not 224.0.0.1 or 0.0.2. We have a special group which is 224.0.0.23, and you can send the version 1. You can see version 1 and 2. You can see that specifically sending to 224.0.0.2 or 224.0.0.1. And again, so you can see that not only sending message to the group, you can include your preference on the source. If you are not interested to nominate the preference for your multicast source address, you can keep it empty as it is operating on the IGMP version 1 and 2. But this has a facility to nominate if you are preferred to get multicast traffic for this particular group from a special source, or nominating it for the security purpose to avoid the rogue multicast sources. Then you can include your source address as well in this version 3 report sending from the host to the first hop router. So this is an example of including the source IP address in addition to the group address in this particular case. Then the router will follow up based on queries, and it's still responding with each and every machine hosted here are responding with the version 3 report, because each and every machine has its own configuration and treated individually, not like version 1 and 2, because you can see that version 1 diagrams, you see that only one report, one responding or suppressing all others. So, but in this case, IGMP version 3, everybody has to respond to the queries, and not only the active ones or the receiving ones only. So its control functionality is a bit different from the IGMP version 1 and 2. So you can see that the IGMP queries sent to version 3 IGMP group 224.0.0.22 respond required to send each and individual host to be communicated for the query as a query response sent by the local router. So because each and every host can have a different state or records or access control lists for its own reference, own purpose. So that's the requirement to respond each and every host separately for the query. Okay, that's about IGMP. Let's go to the further into the IGMP, the protocol of multicast routing, which is the layer 3 multicast, and protocol independent multicast variants. Varieties we discuss. The first, dense mode. Dense mode is the first multicast routing, protocol independent multicast routing available for the industry some time back, and but it's not the usual practice modern day. It's based on the flood and pruning what we discuss. So usually the dense mode it's starting like broadcast. You're flooding the network with the multicast traffic. Then users respond, or the router respond to prune or remove from the group then one by one will be removed. Initially, the traffic will be flooded for all the routers. Then step by step, with the signaling of the downstream routers, they don't need or they don't have receivers to listen this, then it's removed. So this initial flooding is a question, uh, it's an issue for the network. So modern day multicast usually not implemented based on dense mode. Therefore, most of the current day multicast are based on protocol independent multicast pass mode. So the two variants are there. As I mentioned, any source multicast is the first variant of sparse mode, which is required to have route rendezvous point, and there is something called shortest path tree and shared tree included. The three components included. The shortest path tree or source tree, which is from the sources to the rendezvous point. Then rendezvous point, after the rendezvous point, there should be shared tree. All three functionalities included can be used for the any source multicast, which is the usual practice. But more advanced, the modern day ones does not require a rendezvous point. It's only having the shortest path tree, which is the optimal path. So no, there is no shared tree or there is no rendezvous point for the implementation of source-specific multicast, which is the best version currently we have for the performance and the the shortest path perspective as well as the most optimal. The bidirectional PIM, as we discussed, there can be situations like there are multiple the same host can receive and send multicast. In the cases like CCTV or the conferencing, then you need shared tree only because you are sharing both sending and host receiving both functions. So you can't have shortest path tree or source tree only, or the combination of source tree and uh, the shared tree. The bidirectional usually have only shared trees, which is asterisk.g routes are only there. For any source multicast, you can have S, G routes, and source specific multicast, you have only S, G routes. For the shared tree here on the any source multicast, receivers connecting to the what's called the rendezvous point. It's usually asterisk.g, which is mean source not defined, but group address defined. Routes are there, but source path tree and the uh, uh, shortest path, shortest path defined from the source to the rendezvous point, and source tree usually have S, G routes. Hope you remember we discussed details on the few segments there. Let me go back to the slide on the just excuse me on the finding, the exact slide on the route tables need to be. Okay, these are the two slides. I mentioned that the source tree, which is source to, in this case, there is no rendezvous point from source to the destination. There is a clear path, and those are having source S, G routes, which is the source tree. And if you have a rendezvous point, you have a source tree from sources to the rendezvous point. Those are having S, G routes on the routers. Now the router to endorse, you are having shared tree, which are having only asterisk.g routing routes on the multicast route table. All right. That's about the difference between variations to troubleshoot. And PIM source specific multicast have some more advantages than disadvantages. That is the modern way of doing this. Uses simplified the previous process of timers and all those things, solves address allocation problems because by using source specific multicast, you can use same multicast group address for different sources or different the multicast streams. Can use overlapping group ranges. It's more secure in terms of you can implement things like access control list to filter the sources and the segments. The disadvantages require IGP version 3 AVR leaf routers, which implemented with the latest updates of the routers or the operating systems, with the application support for the full functionality. Require distribution of source information to the application. Still, IGP version 3 is backward compatible when you implement it on switches because that's why it's coming by default backward compatible. So this is not really a disadvantage. Requires distribution of source information to the application. So sources can be filtered. The primary application usually one to many applications. The usually source specific multicasts are not recommended for the many to many applications. Like in the case of bidirectional, it is much better in terms of many to many applications, but one to many applications best source specific multicast compared to the any source multicast, which is the predecessor. All right. This is quite important in terms of troubleshooting multicast network. As I mentioned at the initial introductions, multicast routing is dependent on the unicast routing. So to find the shortest path or the best path, you need to implement unicast routing, and then on top of that, you can implement protocol independent multicast. If you are troubleshooting, you need to consider troubleshooting first. Check before any multicast specific troubleshooting. Better to start verifying the whether unicast routing works well, because unicast routing must function to run multicast routing because it's running on top of unicast routing. So even though I mentioned that protocol independent multicast means it's not independent from unicast, but independent from the type of unicast protocol, which means unicast can be implemented by static routes or dynamic routing table, dynamic routing protocols. Irrespective of the way routing protocol, unicast routing protocol independent multicast can work on top of unicast protocol, but that doesn't mean it is independent from the unicast routing, but type of unicast dependent from the implementation type of your unicast routing protocol. So that's the idea behind identification of protocol independent multicast. It's independent from the unicast protocol, but still read unicast routing to be function uh, uh, to operate on the multicast routing. And there is another important aspect, because multicast are usually not protected other than IGMP snooping. They're not protected for the loops, like by default broadcast sending and quite capable of creating broadcast loops. Similarly, multicast usually network devices are we discussed on the bump traffic, the broadcast, unknown unicast, and the multicast at the initially on the last week. So bump traffic usually flooding the network. So then it can create the broadcast or multicast loops, and your network will be unusable if there is the loop in there. To avoid the loop, for the unicast, the switches we discussed on the spanning tree protocol implementation. for the multicast, we have an implementation named the RPF check. That is quite important when we are troubleshooting the multicast network. You need to check whether your RPF check, reverse path forwarding check, is successful. This RPF check recently implemented with the modern day operating systems like Red Hat and SUSE and even Microsoft as well. When you're doing data center implementations, if you have multiple network cards connected, so to avoid the loop, the loop prevention protocols such as spanning tree already there, but certain loopsec like upper layer protocols then can be implemented with the RPF check. Usually, this reverse path forwarding check is necessary to forward from one device to another device in terms of multicast. So reverse path check usually done by the unicast. So what we are testing against is the multicast traffic flows are checked from the sender back down to the path created by the PIM messages. This is known as reverse path for all the received multicast traffic is subject to an RPF check on all the host and modern day host as well as the routers always. Is the coming multicast traffic being received via the interface which I have the route to the source. So what it does is, if you receive multicast from one of the interfaces of the router, upstream interface, it's checking against the unicast routing table whether there is a route to that particular source you receive when you receive by the multicast. So your source, multicast source, check against this thing, what's called the unicast router. So that is called RPF check. That is to avoid loop. So if you received multicast but there is no route, it can be a looping message or multicast looping within the entire network, and it will keep on looping and your network will be unusable. With the multiple flows of the network, your entire bandwidth will be utilized and you are unable to use it for your applications. To avoid, so therefore, it's better to check if we are receiving multicast from a particular message, particular interface, we need to check against the unicast routing table and verify you have a route to this source IP address which are receiving multicast. So if RPF check failed, so if that means if you are receiving multicast from traffic from a source, one of the interfaces of the router, and there is no route to the source, then it will be automatically dropped. Similar to the spanning tree algorithm, your path will be limited to the whatever the interface you are having a route to the source. So this is if your multicast routing automatically configured based on this RPF check process. This is to prevent loops and duplicate packets with the loops. This is one of the ways to minimize the duplicate packets and the loops. So troubleshooting when you are troubleshooting multicast, keep in mind that you need to verify the RPF check by the routing commands we will be discussing on the next week with the specific commands. Okay, this is the RPF check mechanism for if you want more details. So you are connected your receivers and you have your source sending the multicast the channel or traffic to the 234.1.1 and some of the host on the last stop router requesting saying that signaling that I have hosts that want to receive 234.1.1 by using the protocol IGMP. Now you are on the protocol independent multicast. You have two different paths. One of the path is having higher cost considering the matrices. So if you go on the top path, it's have higher cost, which is 10 plus 20, which means 30. You have a lower cost through the 10 dot the bottom path, which are having 10 plus 10, which means 20 costs. So least shortest path must be selected. So if you received let's say in this particular case, now we are sending join request from the first of router, PIM join request to the shortest path next of router. Now next of router look up on the route to the source. Now it can see the route to the next stop, which is the first of router for the source, and it's sending the join message through that path. Let's say somehow there is no route to the upstream route, then it'll RPF check will be fail and it will not forward the join message. So then after sending the join message, now the first of router starts sending what is forwarded from the source to the downstream router, and it will forward back to the first of routers connected to the end host. So RPF check, it is quite usual to run on this particular place. If there is no route to RPF check pass, because the shortest path algorithm or the routing protocol at the unicast selected the shortest path, which is the bottom path with 10 plus 10, which is the shortest cost, lowest cost. There is another path on cost with 30, which is a longer path. There is no route in the unicast route there because selected the best path. So somehow, due to some misconfiguration, if the last stop router received traffic from the top side, then once it verified the shortest path is from the bottom side and there is no route from the upstream side, then it will drop based on the RPF check. This is to avoid, because you have the connected 4 different routers. If the RPF check is not there, then it will loop, traffic will loop among these 4 routers forever. So then keeping multiple streams by looping, your network will be flooded and it is unuseful after the loop. So RPF check is quite useful in terms of forwarding traffic after you receive the join message, and it's tested on each and every router interface, or once it's received from the router, multicast received from the router interface. So keep in mind, RPF check is quite important in terms of your multicast troubleshooting. Without that, I don't think, if RPF check fail, then you need to work on unicast. That's why I mentioned first you need to check whether your unicast routing is working, then you can move to the multicast troubleshooting stuff after checking the unicast routing. Then in there you can check whether RPF check has passed or not as the first step. If your unicast routing are fine. All right, then go to the how to test this multicast in terms of let's say you are a network engineer, you don't have access to host or servers. It is difficult to there are ways to test, but best way to do it do the troubleshooting with your system engineer or the Linux engineer or operating system engineer who are responsible for the host side, because you are sending traffic from one host to another host, which means sources are definitely host, the receivers are again host. So you need to send a better way to do it. For the troubleshooting process, you can mimic the traffic, mimic the sources and receivers by the network engineers. But it's better to do real testing by running an example applications or test multicast applications by mimicking the sender. In this particular case, use video streaming software for PC such as VLC. There is a VLC player which is available to download freely, I guess. So VLC, if you have a video file, in this example, AVI file, you can run in a command line or you can run through the application. It's the desktop application as well. But you can run any video file by using VLC and give your multicast group, in this case 234.1.1.1, and UDP port is 1234, and you have the multicast group address, and you are using the protocol UDP, and you are sending the traffic through the 1234 is the UDP port address for the transport layer or the application layer. Okay, that's something you can do for the source mimicking rather than running real application for the certification. Let's say your application, your network, you are building your network, and you need to troubleshoot your application. So you don't have access to the application, so application teams not cooperating. You can run with a multicast running well, can use this VLC player to mimic the source and define your multicast group address and the port address and the protocol, which is the UDP, to mimic the source. And further, most of the routers supporting the multicast ping. This is not possible to do it on the Linux or multicast. Usually, the operating system is not allowing multicast or broadcast to be sent as ping packet or ICMP packets. It is a security feature, I guess. But routers, for the troubleshooting, people have routers or network devices have limited access and controlled access. You are capable of sending messages to multicast group by using extended ping command on the routers. You can see here, just type ping and give the protocol, which is the IP default. Layer 3 protocol, IP address is the multicast group address 234.1.1, and repeat. You can enable continuous pinging or large counts there. And datagram size you can give less than 1500, which is the maximum transfer unit size, usually default if it is not jumbo frames. Then timeout in seconds, you can put those commands, and extended commands can be implemented, and you can define the interface of the router, and the source IP address can be defined as 192.168.3.2 in this case. And this is one of the ways to mimic multicast source. So you can do it by enabling it on the host, or can do it on the router or network device by extended ping commands to mimic multicast sources. Then you just need to, mimicking the receiver. Receiver can be done in two ways. The receiver side on a PC or the computer, you can implement VLC receiver, and you can nominate the VLC protocol and the UDP, and also you can give this thing what's called the group address. Usually the traditional operating systems or the PCs supported on a Microsoft or Linux or IGP version 2 reports. If you are interested to run on top of IGMP version 3, then you can give source IP address specifically with the VLC player, VLP receive player, and test your systems whether you are receiving from the sources. Once you implemented VLC server on the remote server and other side of your network, you can mimic the receiver on your PC by using the VLC player on the receiver side. Then multicast traffic receiving from the source to the receiver, then you are quite fine with the the implementation end to end from the source to receiver. That is the way you are signing off your usual way of signing off your multicast implementation or troubleshooting your multicast. If your application team inform that there is an issue on my multicast application not receiving the multicast traffic from the source to the receiver, then probably this is the way to run by using VLC player from the source side and the receiver side with these example commands. And you can do it similarly. You run the mimic the multicast source on the router by using extended ping command. The receiver side can be mimic on the one of the routers by implementing these set of commands. On the you just need to select an interface which you assume that multicast is receiving, and you are giving the IGMP version there. If you have a specific, if you know that it is version 2 you're expecting or configured on this particular network device, then you first need to give the IGMP version. Then you need to give a command, mimicking command, which is IP IGMP join group 23 and nominate the group you configured on the other side of the router with the extended ping which you are running on. Now you can receive the messages from this particular group because you are running the source on the other any other router, and if you are receiving multicast, then you're quite sure between the source router and the receiving router you are getting the messages by just mimicking for the troubleshooting for the both side. Version 3 can be done in the same way by defining the source IP address, so that is can be tested as well. So this is how when you are troubleshooting multicast, when you are doing usually when you are troubleshooting the traffic, unicast traffic, you are running a ping command, pinging the remote IP from your source, your machine, to test the round trip latency or the connect reachability for the remote machine. And similarly, you can use trace route as well. But in this case, if you are testing the multicast reachability, you need to mimic multicast source and the receiver by using the VLC application on the host or the extended ping on the routers, so the switches. These commands are useful in terms of when you are troubleshooting in terms of multicast networks. So this is another the example with the scenario. So you have a multicast, already have a multicast source which is up and running and fairly working, and it's connected with the router with the network which is connected to the router C. In this case, it has a bandwidth of 2 Mbps, which is the streaming from the source side, and you have another branch office which is the router A and connecting to the router switch. And receivers are complaining that you are not receiving traffic, and that's your support network engineer, support division or network ops department received an update saying that our branch network receivers are not receiving messages or multicast stream from the source, so media server on the head office side. Now you can start troubleshooting by using some of these commands by statistical. Let's assume that you have no access to the end host, but you have access to these network devices, switches, and the routers. So you can go log into the router and mimic multicast, configure mimicking multicast receiver and check whether you are getting messages from the upstream. So these are the commands by static mimic configurations for the IGMP, because IGMP is the protocol for the communication or signaling between router, between host and the router. Now you are mimicking that this particular interface of the router, which is 192.168.3 range IP address configured on this router interface, and you are mimicking the receipt of messages by configuring joining the multicast group 234.1.1. Then thereafter you can nominate the source if it is IGMP version 3 or source specific multicast implemented. And these are the commands when you are troubleshooting IGMP version 3 implemented with source specific multicast. If your source is already configured and only the configured and sending traffic from the media server, but to your receivers. So you can verify up to the router A level or router A downstream interface level, you are getting the multicast stream. Then it's a issue of switch network or the layer 2 network. Then you can troubleshoot up to the which point you are getting the streams. This is one of the ways to so you can troubleshoot the multicast and configurations and where it's end up. So by configuring this command, you are sending PIM join and then traffic will be coming, and you can check by static configurations for these functionalities for the troubleshooting, even behalf of the local area or branch network users as a network engineer or network support personnel. All right. Okay, more information on the troubleshooting aspect. We need to understand most probable cases, more common cases of multicast problems. Usually, there are 4 types. The source can be having an issue. Is the source sending multicast stream in this case? You can verify whether your source is sending multicast by taking a packet capture or configuring mimicking receiver at the first point, whether you are receiving it or not. So then the most probable can be source is not sending traffic, then receivers can't receive it. It's perfect. It's obvious. There can be situations like source is sending, but receivers are not getting. Can be sure of the receiver's network segment, immediate local area network, or intermediate router issue. Underlying network issue. This can be source issue. If you have a source computer or the source sender computer issue can be one of the causes. The receiving machine can have a misconfiguration or issue on receiving, and there are intermediary network devices can be misconfigured, or RPF check failures or routing protocol misconfigurations can be an issue. And the multicast network misconfigurations are the most probable issue if it is a new deployment, and if it was working fine, then most probably source problem, receiver problem, or underlying network or connectivity network can be the issue. These are the 4 possibilities, 4 major possibilities of multicast problems in terms of troubleshooting aspects. Source not sending, let's address one by one. If source is not sending stream, you can verify on this first of router, in this case router C, verify source is actually sending multicast stream. You can do it by checking the first of router receiving multicast at correct bit rate. These are the commands. Show IP mroute active is the command. It's showing that the group address and the source IP address and the rate which is sending. In this case, it is expected to send 2 Mbps to 234.1.1, and source IP address is 192.168.3.2. Similarly, now if you type this on the router C, you get this message with the speed of the sending speed. So you can see that it's closer to the by average for last 30 seconds. It's closer to 1964, quite closer to 2 Mbps. So it is quite fine and working fine. In this case, source can be verified at the router level. So if you don't have access and you are a system engineer, then you can take a TCP dump on your network, on your server, sending server. A network interface can be nominated. Then you can find out whether you are sending traffic out from this particular server. And if it is a Linux, then quite easily you can run on the TCP dump for the troubleshooting. Then we discussed on the troubleshooting tools, right? So even Windows, you can implement Windows versions of TCP dump. And Wireshark, you can use Wireshark captures. We are having troubleshooting sessions on the Wireshark later of this course. So Wireshark is an open source tool, free, and you can install that and capture the traffic and verify whether you are sending multicast or expected traffic from that particular server. And there is another protocol, simple network management protocol implementations, which you can use for the central logging and reporting purpose with a network management system, NMS. So you can implement NMS system with a SNMP for the troubleshooting purpose. So SNMP trap can be sent based on your criteria. You implemented there for the troubleshooting based on the centralized logging and the reporting mechanisms. So these are the ways to correctly troubleshoot if your source not sending stream correctly to start if you are starting from the source or suspecting from the source. And there can be another issue. I mentioned that usually multicast, since to avoid loops, usually the how far multicast can be traveled can be restricted by using something called TTL, time to live. As we discussed this on the trace route, you can send define how far, how many layer 3 hops you can pass to avoid multicast loops and secure your multicast feed traveling beyond your expected boundaries of your network. So if you put, let's say you have you implemented TTL as 1, then after the media stream server sending it to the first of router, TTL will expire, and then it will not go to the next one if you are defining or TTL on the lower numbers compared to your entire path layer 3 number of layer 3 hops. So it can be tested by using the TTL can be defined usually when you are running this the VLC server for the testing. You can give uh, what's called TTL number as well as an additional command. It's not highlighted here, I guess, but you can define a TTL number. Otherwise, default will be 1 or 0, depending on your application. So you need to give TTL for the application if it's required to traverse longer than 1 hop or longer than your beyond your local area network. So it can be further troubleshoot by using command like show IP mroute to check the multicast routing table. If you are testing on the UDP table, the unicast table, you just need to type show IP route. But in this case, if you are checking the route entries, you need to type show IP mroute. And you can see that IP multicast routing table showing on the router, which is on the router C, which is on the router A. You are testing this, in this case, first testing on the receiver side. So now you can see 192.168.3.2 is the source, S, G route, this case, source source tree. 192.168.3.32 is the media server here, IP address of the source. And you have the group address 234.1.1. So this is an SCMG route. So you have a source and group address as well. It is not on the shared tree. If you don't have a source, then it *.g route, group route. So this is SCMG source route. And you can see the incoming interface. And you can verify whether it should come from this particular Ethernet interface or not. So you can see that mroute is quite active and no active streams. But so routing configurations are fine on the router A or the receiving side router. But let's check on the router C. You can see that show IP traffic and filtered with bad hop count. That's the keyword in here. If TTL expired, you can see that bad hop counts and identify whether your traffic goes from bad hop count increasing. That means the TTL expiration happening on the router C. This is one of the ways to verify the TTL expiration. If you started the troubleshooting from the branch end router, which is the router A, you can verify the routing table configurations, and there are routing tables to receive from the upstream, which is the incoming interface is right, and all those configurations can be verified at the receiver side, branch office router side in this case. And then if it is fine, then you are going on the other side of router and the source closer to the source. And you can see several bad hop counts on the traffic, show IP traffic counts on the filtered count scenario. Then you can see after typing a couple of them, you can see the increment from 949 to 19. 193, 949 to 194, 069. So when you monitor between these two iterations, you can see increment of bad hop count. That means TTL expired there for several packets. So how to recover this? So how to correct it is you need to increase the TTL number from the media server application side. There should be a setting for that. And if we address mainly the source side of issues, like source is not functioning, or the TTL expiration, is TTL not properly set on the source application. And the receiver side issues, we can troubleshoot by debugging for the IGMP. Because IGMP is the protocol communicating between endos and the routers. So in this case, IGMP is quite useful in terms of troubleshooting. And then after if you are not seeing any debug messages or on the IGMP, probably you can capture the traffic or packets. NIFR can be implemented on the receiver to identify the issues by capturing the packets, so sniffing the packets. And we discuss on the source side issues, receiver side issues, and there can be situations like network issues in between. Because of most multicast problems, not multicast, as I initially mentioned, the multicast to be worked, you need to have unicast to be worked. So first, when you are troubleshooting network, if it is not the source, if it is not the receiver side, so you can work on intermediate network devices or intermediate router troubleshooting. Start by checking the unicast routing tables. So that's why he mentioned that most of the multicast problems, it's not multicast. The statement here, why might users report general network issues as multicast problem? Small amount of packet loss, excessive latency or jitter, routing conversions are immediately evident to streaming audio and video users. If there is a audio issue or video issue, usually people report as a network issue, network multicast issue, but most of the time the multicast configurations are stable and RPF checks are there. Changes on the unicast are making many of the issues. So it's better to troubleshoot as it in start from the verify unicast layer or unicast routing layer before we go into the multicast routing. Check for, then you can check for the physical layer issues like, such as interface errors, link congestions, duplex mismatch configurations, the full duplex, half duplex issues, routing reachability. So basic networking need to be followed if there are network issues rather than going specifically at the first stage for the multicast configurations. Okay, still your network can have network is quite good after you verify unicast. Then you, if unicast configured correctly and functioning well, then you can go ahead on the multicast network misconfigurations. So there's something like the multicast misconfigurations can be there is an example here. To verify all internal links have PIM. This case protocol independent multicast pass mode configured. Rendezvous point is configured on all the routers, including the RP itself. So in this particular case, you can see that the rendezvous point is not configured or it's showing is as 0. Because if you are sending traffic from your source machine to the first router need to be configured with the rendezvous point, because that's the next point you are sending the traffic, not directly sending to the receiver. You configured sparse mode, then there must be a rendezvous point. Rather, if you haven't configured rendezvous point, then it's not forwarding to the rendezvous point, and you are unable to send traffic to the receivers through the rendezvous point. So that's misconfiguration of or not configured rendezvous point can be an issue here. And there are things like you can use commands like show IP mroute. So IP mroute is the command usually to check the multicast route. You can see that there is a route in this case *.g. You have, these are not S(G) route, *.g routes, group routes are there. So now you are troubleshooting on the different router which is on the receiving side. So you need to configure both source and receiver side routers with the rendezvous point connectivity. Otherwise, you don't get multicast, or you can't send multicast to that router. The further troubleshoot, you can check. This is another case, the failure of RPF check, which we discussed previously, checking against the check if you have a multicast route. Now you need to check against the next stop unicast route. So if there is no unicast, then RPF check will be failed here. So, but in this case, RPF check pass, and we are having route with a RPF neighbor with definition of IP address. But another group, which is S(G) group 192.168.3.T 224.1.1, that's another multicast route. It doesn't have a RPF neighbor identity or neighbor IP address configured there. So you can see that RPF check failure by there is no not having a neighbor relationship for this particular router in the incoming interface. So then you need to troubleshoot on why RPF check failing, and probably the unicast route or the other areas can be troubleshoot further with the configurations. So all these scenarios, it's quite useful on the routers to use show IP mroute, and there are several filters you can put show IP mroute count and all those sub filterings are possible, not only the major command, but all the filterings are possible with the pipes. This is the pipe sign, can filter after that with the criteria implemented. This case including RPF failed or other messages with the output. All right. So then now we can start on the other areas like multicast routing, the router to router signaling, protocol independent multicast. So we discussed initially on the source issues, the receiver issues, which are two computers, which can be computers. Now we are discussing on the network issues and the router issues related to the network. And the unicast should be work, and multicast configurations can be there. There can be situations like router to router, protocol independent multicast pass mode implementations issues. So this is another example. So we have a problem here. The receiver just told me the group it wants to join, but didn't identify the source. So in which direction is the upstream router? There is a question on this troubleshooting stuff on the implementation of protocol independent multicast pass mode implementation. You have bunch of the first IGMP membership, bunch of users, multicast receivers connected to a switch, and now we are communicating through the IGMP, and now the source is sending multicast, but the router is sending where is the source for the giving a message. It is unable to connect with the source to receive multicast and send it back to the receivers. So IGMP message does not include the identity of the multicast source. So you can see that the receiver sending, it's intended to join 234.1.1 group address, and its IP address is 10.1.1. You are sending to the destination, which is the reserve group, to communicate with all the host and routers, which you are sending the report with the expression of intending to join the group. The IGMP message does not include the identity of the multicast. So you are not giving the multicast source in this case. So if it is IGMP version 3, you can give IGMP version the source IP address and restrict it. If you are troubleshooting IGMP version 3 on top of PIM sparse mode, this can be a common situation. So you don't need to give the source address, but if you are mandated or to give it based on the security implementation by ACL, so it can be implemented on the source specific multicast, and this can be blocked if you haven't implemented by using the IGMP version 3 and nominating the source for the particular group. So it is a kind of the implementing the security, and it can be implemented by using IGMP version 3 in this case. And then rendezvous point, I will discuss details on the protocol independent multicast intermediary point, which is the rendezvous point RP in the short term. The PIM source sparse mode uses the router called rendezvous point. The sole purpose of rendezvous point is to allow the first hop router, which is connected to the multicast source, to find out IP address of the source. Rendezvous point first hop router to find out IP address of the source for the particular group. This is in this term, first hop router is the receiver connected first hop router required to find out the IP address of the source for the participant group. So sole purpose of rendezvous point, you need to, so in this case, you need to configure, if it is not IGMP version 3, you need to configure rendezvous point. It can be another router to find out the source connectivity or source IP address given by usually the rendezvous point to connect with the source tree. So somehow somebody has not configured, the network configurator not configured the rendezvous point IP address on this. Okay, just give me a second. Not configured the rendezvous point on this on this router connected to the receiving network. So the receivers don't know the source address and don't care. It's the term any source multicast because it is not IGMP version 3 or source specific multicast because it's not sending a source IP address. So it is mandatory to give rendezvous point IP address for the configure PIM sparse mode. So if you are not doing this source specific multicast and IGMP version 3, and if this is IGMP version 2, and you are running the any source multicast, which is the sparse mode, and this particular router need to be configured with the rendezvous point router's IP address. In this case, they forgot to configure, or somebody who's configured the network forgot to configure the IP address of the rendezvous point. So it is necessary to configure rendezvous point on all the routers on the other on the network other than the RB. That is one of the cases, one of the example cases. So first you need to check whether this is on IGMP version 3 and source specific multicast. If not, if it is IGMP version 2 and any source multicast with the sparse mode, this is the way you need to think in terms of troubleshooting. This is one of the examples. So another representation is the rendezvous point in this case. So let's assume that network engineer configured a rendezvous point 192.168.0.1, which is an intermediate router in the network. And once you receive the IGMP request from the host and via the switch, then first of all router or the router connected to this network segment of receivers, if you configured rendezvous point, it will definitely forward it to the rendezvous point, which is in this case 192.168.0.1. So traffic will be forwarded by the source to the rendezvous point, even though so this is the way it's connecting. So now rendezvous point has to be registered for this particular group because it's now where the source machine or source computer and the first of router from the source side already have a already trying to send traffic, and the registration process will be there to merge the two trees of the request and the source. So you can see the shortest path is still on the downstream or bottom network on the middle network, because higher cost is there on the top. 10 plus 20 is 30, 10 plus 10 is 20. So the ideally unicast should be the best path for the unicast is this bottom path, but still we configured rendezvous point on the top. So then then you can see that there is a message saying that I don't know the source IP address for 234.1.y. If you haven't configured, this is message by because there is a request to join from the receiver side up to the RP. Now RP saying that I don't know the source IP for this particular group to join you. Now the source is trying to send traffic, and there is a registration process with representing the dotted line. Initially, it will send unicast traffic for the initiation. then to join with the RP. Then there we don't go into that's finer detail. I just wanted to give you a representation how the multicast sending from the source side. Now it started sending the RP. Now it's sending the register stop once the multicast channel established and receiving traffic, because it's initially registering with unicast, then only moving to the full multicast traffic in terms of usual process to make it perfectly reliable in terms of protocol operation. So now you can see that the multicast traffic is sending to the RP, and RP can forward back to the first of router or the last of router which the receivers are connecting. I finally know the source for the 2.3.4.1.1. So it's a misconfiguration based on the situation, because RP IP address not configured on the last of router. So now it's fixed, and this is the way after you configured rendezvous point IP address on the last of router of the receiver side, you are getting message. Now you have a this is about rendezvous point. Now you have the larger another issue. As I mentioned, the shortest path is not this, because you are sending multicast through the suboptimal path, which is having the cost of 30, even though you have a shorter path which is on 20. So you can further optimize. This is by different way because you have implemented rendezvous point on a suboptimal place, which is having a higher latency. You can do a couple of things. You can configure your rendezvous point here to optimize based on your overall topology, if that is the only requirement to have, and you can further work on implementing something interesting because the PIM's passport have something called shortest path tree switchover, which means initially you are getting traffic to the suboptimal rendezvous point path. Once the first packets received, the last of router can switch over to the best path based on unicast implementation, unicast routing table. That feature is their modern day net routing table or modern day PIM sparse mode implementations. It automatically, after the first few packets, then it will automatically switch over to the best path. So then there is no suboptimality there onwards, because you are receiving multicast from the shortest path. So that is that feature of PIM sparse mode named as shortest path tree switchover. That is usually happen on the last of router, no intervention on the first of router connected to the source. So you can see, you can understand there are two features. Rendezvous point we usually have to implement with the PIM sparse mode, and the modern day networks now have a shortest path 30 switchover implementations. You are not getting traffic from the longer paths. Now only the first few packets, even you misconfigured RP on a suboptimal place. After the first few packets, it will switch over to the best or the shortest path based on your routing algorithm or routing protocol implemented between the routers. So that's called shortest path tree switchover. When you are troubleshooting, these features are quite important. You can see whether it is switched over, you are on the shortest path, and these features and knowledge is quite important in this case. So this is the process of moving to the shortest path for your information. Now the ones while switch automatic switchover, you are getting duplicate messages from the two path. Then it will automatically the last of router remove or pruning or disabling one path by pruning signaling. So then it is not, you are not getting duplicate messages based on the duplicate routing or the multiple network paths. Okay, this is the last slide for today. PIM sparse mode rendezvous point discovery can be, this is the example configuration of the correction. You just need to configure on this last stop router. If it has not configured the IP address, PM, RP address on the next stop router, which is 192.168.0.1. This is the case we were troubleshooting. We were troubleshooting that hosts are not receiving multicast, and you identified that you haven't configured, you implemented PIM sparse mode with the IGMP version 2, and you haven't configured IP address of the rendezvous point on this last of router. There is no way to find out exact source because you have no configuration on the direction of rendezvous point. This is the way to add this command of rendezvous point. You just need to log in into the configuration mode of the router, and you need to configure all the routers to directing the rendezvous point by this command IP PIM RP address and the IP address of the rendezvous point, in this case 192.168.0.1. And you can have an option of dynamic RP configuration. There are several protocols. The famous ones are, one of them was Cisco proprietary Auto RP. If you are not adding statically this thing, you can implement this by using dynamic RP configuration protocols such as ARP on all the routers to point out the exact rendezvous point. Because if we are changing the rendezvous point, it will change dynamically by using these protocols. That the first one is Auto RP, which is the Cisco proprietary. Another IETF standardized protocol for all the vendors is Bootstrap Router Protocol, BSR, that is based on the standard of RFC 5059. So this is how you resolve the issue, what you identified on the troubleshooting as an example, on the rendezvous point not configured. And when you are not, initially you received a message from the user saying that they are not getting the multicast. So what if receivers knew the source from the start? That's IGMP version 3. So we'll be, okay, probably I can finish it off. Okay, IGMP version 2 and source, the protocol independent multicast sparse mode, which is the one we discussed on the previous example. So let's assume that the issue has reported from this, the first, give me a second. Issue has reported here from the people who implemented IGMP version 3 and the source specific multicast on the route as the multicast routing protocol. If that's the case, then troubleshooting, this is how it's handled. Just give me. Okay. This is how. So if you are implemented IGMP version 3 on the receiver side and you are unable to receiver side, then you can define, you don't have to worry on the troubleshooting stuff because this issue will not be there, because by default you can give source IP address in advance by using IGMP version 3. You don't have to depend on the rendezvous point. There is no necessity on the rendezvous point due to this reason for the IGMP version 3 plus source specific multicast implementation. So you can just give your group address on the IGMP version 3 page and the destination IP address, which is the control plane protocol. The source IP on of the server can be defined as well if necessary. Then you can see that it is quite capable of handling by the first of router or the last of router on the perspective of IGMP version 3, and it will definitely connect with the source by automatically based on source specific multicast implementation. So IGMP source discovery, you don't need rendezvous point as an intermediary point to find out exact IP address of the rendezvous point to find out the source address from the group. So you don't need the assistance from the rendezvous point. You can predefine your source address by using the IGMP version 3, and it's quite easy, and you can omit the suboptimalities on this the path and select the shortest path by using the IGMP version 3 and the source specific multicast jointly together. So that's about the troubleshooting stuff. And finally, the receiving side, you can see this is an example of how does the receiver knows the source address of the each group. If you have multiple groups, like let's say there are bunch of groups, 1, 2, 3, 4, 1.1, 1.2, 1.3, and 4 is there. There are different multicast sources for each one. For an example, let's say your POTV from Sri Lanka Telecom. Surely it's the set-top box installed there, which is having the remote access capability. If you type 1 on your remote device, then set-top box will do is it has the list of channels mapping the multicast group to the source addresses. So it will send communicate with the set-top box management server hosted on the SLT data center, and sending it the message to download the file list with the channels, multicast channels mapped to the sources. So each channel has mapping to on that particular file has each channel mapping to the source. So if you want to see the channel 1 by clicking 1, then it will automatically reach the 192.168.1.1 based on the channel list downloaded from the STP management box to the set-top box. So this is how you are changing the channels and without knowing the IP addresses of the servers, because set-top box just automatically downloading it from the management server, and you have a mapping inside there with a static mapping. This can be improved with the dynamic mapping as well. So this is another example of how to statically map if you are not using the dynamic protocols for the applications. So this is that's about today. So we will be discussing I'm planning to complete the multicast troubleshooting as well as the multicast security best practices on the next week. Then we can start on the time synchronization and time stamping from there onwards as the next session after the multicast. Let me start preparing the assignments. If you have questions on assignments, you may ask now, or just reach my by using my emails, or probably you can ask questions on the next time as well. So let me update this. Any questions on until?
Yes, just one clarification. Is it okay to have much lengthy answers than a half a page for questions that you are asking that?
Yeah, that's the minimum. I prefer having longer answers, because if you let's say as a guidance, if you write if you describe the answer the question within a half a page, which addressing the question, still you can get the full marks if you have answered correctly.
Okay,
But if it's require more than half a page with the diagrams and all those things, so you are quite sure that you answered fully. So then you get full marks. So it's better to have longer answers than short answers, or restricting it to half a page. Our guideline was to have at least to have half a page minimum, because without giving the one sentence answers or something like that. So these are essay type questions. Most of your exam questions are somewhat similar to this. You are getting the pages for exams, you are getting a space defined, but for the assignments, there is no definitions other than the minimum length. So you can answer more than half. There is no issue on that. It's much better, longer answers, and I have no issues on that. Again, you can include diagrams and the flow charts. That's much better. Then we can understand that you know the stuff and you attended to the lectures and all those things are there. So you don't have to limit on half a page. That's the minimum limit. So hope that answers. Any other questions?
Okay, sir. Thank you, sir.
All right, welcome. All right, so let me update this on the evening. Then if you have any further questions, just clarify with me. So we have done the different traffic types and the multicast fundamentals, and we stepped up on troubleshooting on today. And next week we are on the multicast security, and if time permits, I can start on some sections of time synchronization and time stamping for the troubleshooting. Right. Thank you very much for joining the session. Let's meet up on the next week. See you again.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. Thank you, sir.
Thank you, sir.
You're welcome. Thanks.